Okay, so let's go ahead and get started. Today I'm going to look at the section 10.2, which is on what's called the regression line. Now, you may remember last time we started talking about bivariate data, um, where we have a bunch of ordered pairs in our sample. And the example we looked at last time, um, we had we sampled four. Well, we had this, I guess, this big rectangular sheet of chocolate chip, a big chocolate chip cookie that's rectangular, and we were talking about uh, we sampled four cookies. The first one was a 1 inch by 1 inch cookie, and then we counted out how many chocolate chips were in that 1 inch by 1 inch square cookie, and it turned out to be two, right? And then we got a 2 by 2 inch cookie or square 2 inch cookie and found out there were four chocolate chips in it, and then 3 inch square cookie had six, and a 4 square inch cookie had eight. Essentially, what we did is we sampled four different size cookies, and we counted up how many chocolate chips were in each of those, right? So X represents the size of the cookie in square inches, and Y represents the number of chocolate chips in that particular cookie. And so we have what's called bivariate data. Um, Essentially, bivariate data is a case where you have ordered pairs, two variables X and Y, but they're matched. Okay, they're matched pairs. Now, of course, we're sampling this from a larger population of ordered pairs. Population would consist of conceivably any square inch, you know, any size cookie, square inches, measured in square inches, and then the Y value would be the corresponding number of chocolate chips in that particular sized cookie. But so we're randomly sampling four from this population, and this is what we got. Okay, and then so one of the things we wanted to do was determine whether this, if you were to plot this on a scatter plot, um, would it form a straight line? Um, and we did do a scatter plot for this, and we did notice that it actually formed a straight line. The way we sort of calculate that is with this little formula down here called the linear correlation coefficient. Um, and so for a sample, we call this R. And we went ahead and calculated this last time, plugged in all the numbers, and we found R to be 1. Remember, R is always between 1 and -1. If R is 1, it means it's an uphill line. If it's close to -1, then it's a downhill line. And then if R is 0, that indicates that there's not a line at all. Of course, R could be any number between -1 and 1, so sometimes it's difficult to tell whether it's close enough to be called a line. So if R is 0.8 or 0.7, is that forming enough of a line to say that it's going, an uphill line? Likewise, it could be -0.6 or something like that, and is that close enough to -1 to say that it's a downhill line? And so we actually have a formal hypothesis test to see whether we have a linear correlation between the two variables, X and Y. And we actually ran this test last time. So this is, how you set up the hypothesis test. It's a claim about rho, and if you remember, rho is the linear correlation coefficient. If you plug in every ordered pair from the population into this formula, so rho would be the number that you get for all the ordered pairs um, plugged into this formula here. And so the claim is whether rho is, rho is either 0, which is the null hypothesis. And if that's the case, then there's no linear correlation. And if rho is not 0, then that indicates that it's, either 1 or -1 or close to it. And that means there is a linear correlation, and that's the alternative hypothesis. And so we went ahead and formally ran this hypothesis test at significance level of 0.05. And we a test statistic that was really large. It went way past the critical value when we did the traditional method. And the p-value for this test statistic turned out to be so close to zero that it rounds to zero. So it's a really, really small number, but like 0.00000000001 or something like that. But effectively, it was zero. And so we decided that if the p-value is less than the significance level, then you reject the null hypothesis, and that's what happened in this case. So we rejected the null hypothesis, and that means there's evidence of a linear correlation, which we already knew because when we calculated R, we got 1, and 1 is a perfect line that's going uphill. So anyway, the point is that this forms a line when you make a scatter plot of it. This data here from our sample forms a line. And so this section is about, okay, now that we know that we can model this bivariate data with a line, we're going to try to figure out what that line is so we can make predictions about other x values that we may run into in the future. So what about a 1.5 square inch cookie? How many chocolate chips would we expect to be in that size of cookie? And of course, you can look at this and tell that it's going to be between 2 and 4, so you might expect it to be something like 3, right? But anyway, we're going to find a line that best describes what's going on with this bivariate data. And that's called a regression line. Okay, so a couple of things here. We're going to use the point slope formula, or I'm sorry, the y-intercept formula for a line. And you may remember this from algebra. One way of describing a line mathematically is with this y-intercept form. So y is equal to mx plus b. M is the slope, and b is the y-intercept of the line. Except we're not going to use m and b in statistics and stats classes. They call this one, well, if it's coming from a sample, this is called b1. The slope for, if it's coming from a sample, the slope is called b1, and y-intercept is called b sub 0. So if it's coming, if it's coming from sample data, that's what we call it. But if it's like coming from a population, we call the slope beta 1, the fancy b beta 1, and the y-intercept is called beta sub 0. And notice we do have a different symbol for the y value. The x value is the number that you're going to make a prediction for. So what would be a prediction for x? So you would say, what x value am I trying to make a prediction for? You plug it into here. And then the best predicted y value is labeled as y hat, y with the caret on top. So y hat is a predicted y value because it's based upon the sample information. The actual y value we label with a y. So if you're talking about a population, then the line would be written like this, right? Y is equal to beta 1 x plus beta sub 0, where beta 1 is the slope, where you're using all the information from the population to get the slope, and beta 0, the y-intercept, is coming from using all the information from the population to get that y-intercept. That should give you the actual y value, so we call it y. That's not what's going to happen in most cases. We're not going to have all the information from the population, so we're not going to know beta 1 or beta 0. What we're going to do is look at the sample information and come up with, from the sample, we're going to come up with a slope for our regression line. It's going to be called B1, and then the y-intercept is going to be called b sub 0. So I just want you to be aware of the notational difference here. This refers to a regression line. It's called a regression line. This is about basically coming from the information from a sample. whereas this one is a regression line. It's based upon information from the population. Okay. So anyway, if you look at the example we did last time, this is our sample data. So we're gonna find the regression line that fits this data. So we can use it to model, like we're gonna model the behavior of the bivariate data with a line. Now that we know it's a line, right? We determined last time that R was equal to 1, so we know it's forming a line. So now we're gonna actually try to figure out what line best describes this bivariate data. Okay, and so the way we do that is there's just a couple of formulas we need. This is going to give us the slope B1, and this is going to give us the y-intercept B sub 0 for our regression line. So I'm just going to plug it into the numbers into this formula and figure out what they are. Okay, so this says we have to take this sample size n, and if you remember, it was 4, and we're going to multiply it by the sum. Remember, this means sum. The sum of x times y. Okay, so we did this last time. These are our x values, these are our y values, and then what you do is you take x times y for the ordered pair. So you say 1 times 2 and you get 2, 2 times 4 you get 8, 3 times 6 you get 18, 4 times 8 you get 32. And then you're supposed to sum up these values, right? That's the sum of x times y. So you just add these up and you get 60. So this summation here is 60. So we got 4 times 60 minus sum of the x's times the sum of the y's. So when you add up the x values here, this column adds up to 10. So that's the sum of the x's. And then when you add up this column, it adds up to 20. So that's the sum of the y's. So you're going to get 10 times 20 for that second part. And then again, notice that the sample size is 4, right? So n was 4. Okay, so n was 4, this was 60, and then this was 10, and that was 20. Okay, again, the sample size is 4. And then this says sum up the x's after you have squared them. So we did this last time. Here's our x values. We're going to have to square each of them. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And then we're supposed to sum up these values here, right, after we've squared the x values. So if you add up this column, you got 30. So that's the sum of the x's after you have squared them. So that one is 30 times 30. And then minus sum of the x's squared. And that's different than the sum of the x's after you have squared them. Those are two different things. This says add up the x's first, and then when you're done adding them up, you square that number. This says square the x's first, and then add up those numbers. Okay. So when you add up x values, we got 10, right? So the sum of the x values is 10, and then we're supposed to square that number, so this should be 10 squared. Okay, so basically that's how the formula works. So if you multiply this out, you get 240 minus 200 over 120 minus 100. 10 squared is 100, right? So notice you get 40 over 20, and that's just equal to 2. Okay, and so now we know the slope of this line, the regression line. And remember, the regression line is trying to model the bivariate data. So we can make predictions for x values that we don't know the y value of. So we now know B1 is 2, the slope, right, times x, and now all we need is the y-intercept, B sub 0. Okay, and this is the formula for finding the y-intercept sub 0. Take the sum of the y's. The sum of the y's was 20. The sum of the x's squared. Let's go back and look at that. I forgot what it was. Sum of the So the sum of the x's after you squared them, that's 30. And the sum of the y's was 20, right? So this was 20 and this was 30. The sum of the x's was 10. And then the sum of the x's, or the sum of x times y, right? So you say x times y and then sum those up for each ordered pair. And that added up to 60. Okay. And then times the sample on the bottom. So that's the top number. And then the bottom number, you know, take sample size times the sum of the x's after you've squared them. And that was 30. Then this is the sum of the x's, and then you square that number. And that's a little different. That was sum of the x's is 10, and then we square 10. So this should be 10 squared. Okay, and so it looks like we get, okay, 20 times 30 is 600, and 10 times 20 is, oh, sorry, 10 times 60 is also 600. So it looks like you get a 0 on top. On the bottom, you get 120 minus 100, so that's just 20. All right, so you get 0 over 20, which is just 0. Okay, and so that says our y-intercept is 0. And so this is the line that best describes the sample data that we got. This was the original sample data that we had, right? It was this. I think it's pretty clear that it should be 2x, right? If you look at this, and someone said, what is, if x was 1.5, what would you predict y to be? You would predict it to be probably 3, right? Because it's between the 2 and the 4. And you can see the pattern. It looks like the y value is always twice as much as the x value. And that's exactly what this line describes, right? It describes the behavior of these ordered pairs. Okay, so anyway, I'm going to show you this on the calculator. One thing I want to caution you about, though, is to be very careful about this. Now, the reason we're doing this is because we can look at the sample data and come up with if there's a linear correlation, first of all, right? So you've got to check that there's a linear correlation between the two variables. We did that last time. R was 1, right? I mean, that is a perfectly uphill line, right? So there's no doubt that it's a line. So you got to check that first, though. Got to do a hypothesis test and make sure that the sample data that you have actually can be described with a line, right? That you can model it with a line and it would make sense, the scatter line. So make sure you do that first. But once you know this kind of forms a line, then you can find the regression line, use it to make predictions for x values that you don't have. So again, what happens if x is 2.5? Well, my best prediction would be plug 2.5 into here, and my predicted y value would be 5. And remember, this is the predicted y value, so that's why we put a little hat on it. This is my predicted y value. Actual y value, I mean, this is predicted, right? This is a prediction. The actual y value would have to come from the population. So we'd have to go back to here and select, make a cookie that I guess would have 2.5 square inches, cut it out, and then count up how many chocolate chips are in there and see what it is, right? It may or may not be 3, but whatever it is, this is the actual y value. And in lieu of doing that, let's say we never cut out a 2.5 square inch cookie. If we never did that population, then we could make a prediction for it. And this is our predicted y value. So those are two different things. This may not be correct, right? This is just a prediction. It's our best guess as to what y would be, right? When x is 2.5. So just be aware of that, okay? So I'm going to show you how to do this on the calculator real quick. So we kind of did this last time a little bit. I'll show you some other things we can do. You want to go to Stat, and then Edit, and just make sure you put bivariate data to L1 and L2 and make sure that they're matched up accordingly, right? So 1, 2, 2, 4, 3, 6, 4, 8. Okay. And just remember, I put the X's in the first column and the Y's in the second column. Okay. And then go to Stat and now Tests. And then we did this last time. You can go to Linear Regression T-Test. And then you can check, right? X is in L1, Y is L2. Keep the frequency at 1. And then when you run your hypothesis test, remember the alternative hypothesis is that rho is not 0. So just keep it at that. And then we calculated it, and this is where we got our test statistic, 1 times 10 to the 99th power, which is just 1 followed by 99 zeros. So this was a really big number. The p-value was 0, right? And this is how you can test and see whether it's a line or not. And so this is, p-value was less than alpha, which we tested at 0.05. And if the p-value is less than alpha, you reject the null hypothesis. And that's how we decided that it was a line. Because if you look back at the hypothesis test, oh, I think I just lost it. Okay. Let's see. No, there's okay. So this is how you set up the hypothesis test, right? So if you reject the null hypothesis, rho is equal to 0, then you're supporting the alternative, which says that rho is not 0. And that indicates that you have a linear correlation, because if it's not 0, then it's either -1 or, well, it doesn't have to be -1 or 1, but we're thinking that it's close to -1 or +1 because it's not close to 0, apparently. And that's what happened, right? So anyway, this is how you can test it, right, on the calculator. Just look at the p-value, compare it to alpha, and see what happens, okay? If the p-value is less than alpha, then you reject the null. If the p-value is greater than alpha, then you fail to reject the null hypothesis. Then once you know what the line, so again, make sure you test to make sure that your bivariate data, when you put it into a scatter plot, looks something like a line. You've got to test it first, right? Doing a hypothesis test. But once you're confident that it forms a line, then you can find the regression line and use it to prediction. So right here, the regression line is given at the top. Um, it should say Y with a hat on top, but the calculator doesn't put the hat on top of the Y, but it's Y hat. And then they label these a little differently. Label the slope as a B, the y-intercept as an A. And so down here, they give you the A and the B, right? So B is 2 and A is 0. That's exactly what we got, right? Because if B is 2, then you get 2x. And if A is 0, then it's 2x plus 0. That's just 2x. So we end up getting the same thing, okay? And in fact, this is the scatter plot right here. You can see the graph of the scatter plot. Now remember, we did this by going to stat plot, turn on the stat plot, and then select. Now if it's off like this, just make sure you turn it on. But then you go down to the type of stat plot that you want, and we wanted a scatter plot, right? So we picked this first one here, right? That one's a scatter plot. And this is the scatter plot. 2 comma 4, 3 comma 6. I'm sorry, 1 comma 2, 2 comma 4, 3 comma 6, 4 comma 8. So there's our sample data. Okay, put into a scatter plot. And then the way you want to check and make sure that this is correct. X is L1, right? Y is L2, and then just pick whatever mark you want, and that'll give you the scatter plot. Then what I'm going to do is I'm going to go to Y equals. Of course, you could graph this, right? Put it up here if you want. Just press graph. Then I'm going to go to Y equals, this button over here, and I'm going to type in the regression line that we just found, 2x And then I'm going to go back to graph. And now it's actually going to show us the regression line on top of the scatter plot. And you can see it's hitting every single dot. So this is a data that we got forms a perfect line, and this is the line that it forms. This is the regression line. Best fits the data. Okay, and that's pretty much what this section's about, is once we know that we have bivariate data that forms some kind of line, then we're going to find the regression line. And once we have the regression line, we can use it to make predictions. You give me an X value that you want to know, make a prediction for, I can plug it into the regression line and get my best prediction for the Y value, which we call Y hat. So I guess what I want to do just from here is let's look at the homework, and I'll show you, how to work out some of the ones in the homework. Okay, so here's another example from the homework. This is number 7 from 10-2. And what they've done here is they've taken blood pressure measurements from the same woman. They took her right arm blood pressure and then her left arm. So they put the cuff on her right arm and measured it, and then they immediately put it on her left arm and measured it at the same moment in time. So the first time they did this, in the right arm it was 103, and in the left arm it was 177. And then they probably came back sometime later and did it again for the same woman. They found her right arm blood pressure level and then her left arm blood pressure level. And so apparently they did this a total of 5 times. 1, 2, 3, 4, 5. So we have this is our sample, right? Our sample size is 5, but it's ordered pairs, right? Matched pairs. So it's bivariate data. I guess we'll call X the right arm and Y the left arm. And what they want to know is find the best predicted blood pressure for the left arm, given that someone has a blood pressure of 90 for the right arm. We're going to try to predict what your left arm blood pressure level would be or for this woman probably, if it were 90 for her. It's particular to this woman, right? So you can't expand this beyond anyone but this particular woman. And so wait, there's one thing we need to take care of here, first of all. Notice that they're trying to predict the blood pressure in the left arm given the blood pressure in the right arm. So this is what's important. One that you're given is the right arm, and that's called the independent variable. And the independent variable is always X. So X is the one that you're going to plug in, and Y is the one that you're going to predict. So when you look at this, the right arm is going to be X because that's the one we know, and the one we're predicting is going to be Y or Y hat, which is the left arm. So just be careful about that. So when you look at your data here, regardless of how they've written it, X is going to be the right arm because we know we're predicting X, Y when X is 90, and left arm is Y because we don't know that one. Okay, so that's important. But before we do this, we need to make sure that this sample of bivariate data forms something of a line. Because if it doesn't form a line, then you are not going to use the regression line to model it. It doesn't make sense to model it as a line, like with the regression line, if it doesn't form a line. So we've got to run a hypothesis test and make sure that it forms a line first. So I'm going to go ahead and just do this on the calculator. I'm going to go to Stat, Edit. I'm going to clear out the first column, put the X values in L1, 103, 102, 94. And then 79, and then 80. So those are my X values. Okay, and then I'm going to put the y values in L2, but make sure you match them up correctly. So 103 is matched with 177. Just make sure you put them next to each other. And 171 and then 145. And then finally 144 and then 145 again. Okay, so there's our bivariate data. Let me take this off. And then, like we did before, go to stat and then tests, and then scroll down to linear regression t-test and make sure, X is L1, Y is L2, the frequency is 1. We're testing with a alternative hypothesis of rho is not 0. Now remember, you could do less than 0 or greater than 0. If it's less than 0, then I guess you're claiming that the correlation it's a negative correlation, so that R would be a negative number. And if you're saying it's greater than 0, then you're claiming that has a positive correlation, so R would be positive. Not equal to is that either way, it could be close to 1 or -1, but it's not 0, right? And that's exactly the way you set up a hypothesis test here. Okay. Remember, 0 means there's no linear correlation, and not 0 means it is a linear correlation because it's like 1 or -1 or close to them. So anyway, and then calculate it and see what you get. So the test statistic now is 2.95. Let me write this down. So I guess, here's the formal hypothesis test. Let's write this down first. Again, this is the same. Rho is not 0, rho is equal to 0 here. This indicates no linear correlation. This one indicates that there is a linear correlation. Okay, and you could do the traditional method or the p-value method. Let's just do the p-value method this time. And I don't know if they gave us a level of significance to test that or not. Yes, so they say use a 0.05 significance level. So I'm going to test at 0.05. Okay. Now remember, there's actually two ways you can do this. I'm doing the formal hypothesis test that we talked about last time. When you run a formal hypothesis test, you could either do the p-value method or the traditional method. I'm just going to do the p-value method here. And so you find the p-value and you compare it to alpha. And p-value in this case is 0.06. Okay. And then if you're doing the p-value method, you just take the p-value and you compare it to alpha. And in this case, p-value is greater than alpha. And if you remember, when this happens, you fail to reject null. So if you fail to reject the null, means that this hypothesis is reasonable. Rho could be 0, and that means there may not be linear correlation. Okay, so the conclusion would be there's not enough evidence, right? Let's just say there's no linear correlation. That would be our conclusion. Okay. By the way, if you did the traditional method, we get the same result. With the traditional method, you would find the critical value that goes with alpha. By the way, it's a two-tailed test, right? Because of this, you would divide this up evenly into two tails, 0.025 in each. And then this is a t-score, and our test statistic for t from the calculator was 2.95 if you round it off. So that's our test statistic. Then you would compare the test statistic to the critical values here. This one would be positive, of course, and this one would be negative. And you'd have to look this up on a t-table, which I'll go ahead and do. I'll pull one up off the internet. Okay, so we're testing at 0.025 and one tail, which would be this column here, or 0.05 and two tails, whichever one you want to look at. It's the same column. And if you remember, the degree of freedom in this case is 2 less than the sample size. In the past, it was 1 less than the sample size, but because we have two variables, x and y, subtracting 2 from the sample size. And if you look at the sample size, I believe it was 5. Let's see, 1, 2, 3, 4, 5. So this is going to be 5 minus 2. So we have 3 degrees of freedom. And so you're going to look at, again, this column here, 0.025 in one tail or 0.05 in two tails at 3 degrees of freedom. Looks to be about 3.182. And this one would be, of course, negative 3.182 because it's symmetric. Okay, and this side's negative. So those are your critical values. And you can see that the test statistic lands just short of this critical region, right? And that's your test statistic right there. And so, if you don't land in the critical region, if the test statistic does not land in the critical region, then you fail to reject the null hypothesis, and we get the same answer here, right? There's no linear correlation, apparently. Regardless of which way you do it, you end up with the same result. Okay. Now, what does that mean? It means the regression line is not a good predictor for the behavior of this scatter plot. So you would not want to make predictions on using the regression line. The regression line is not modeling what's going on here. Nonetheless, I don't know why MyMathLab does this. Nonetheless, they still ask you to find the regression line, right? They ask you to find the slope and the y-intercept. Apparently, the slope is 1.2 and the y-intercept is 45.9. I don't really like this because the regression line is not valid in this case. There would be no reason to find the regression line if the data does not form a line. And we've already tested it, and we did a hypothesis test on it, and it doesn't form a line, right? There's no linear correlation. So in the real world, you wouldn't find this regression line because you're not going to use it to make predictions. But nonetheless, if you did find the regression line, here's the slope, 45.9. Not the slope. A is the y-intercept, 45.9 is the y-intercept, and 1.2b is the slope, right? And that's where they got those numbers right here. Now, this is a little tricky, so I want you to be very careful about this in the homework. It's the regression line. They ask you to find the regression line, and then at the very bottom, they say, given that the pressure in the right arm is 90, make a prediction for what it would be in the left arm. And it's very tempting to plug 90 into here and see what you get. That's not how you make a prediction in this case. The regression line is not modeling the sample data. It's not linear. this does not form a line, right? If you make a scatter plot of this data, it's not forming a line. That's why we did the hypothesis test. So if the regression line is not modeling the behavior, and unless you know of a better way of modeling what's going on, which those are more advanced uh, classes, like it could be quadratic, it could be a parabola, okay? But we're not going to do that in here. So for us, if it's not linear, and the best prediction would be the average y value. We're just going to simply average up the y values. That's kind of saying that the x value doesn't matter. Uh, right? If the x value doesn't matter, then what would you use? What would you predict for the y value? You would just say, well, if x value doesn't matter, then I'm just going to average up the y values. The average y value. That's my best prediction because if x doesn't matter, then I just want average y value. So think about it this way. I mean, if the right arm blood pressure affects left arm blood pressure, then in a linear fashion, then we would have used the regression line. Apparently, it doesn't, according to the sample data. So then you ask me, what is her left arm blood pressure level? I don't care what her right arm blood pressure level is because apparently it doesn't affect the left arm. And I would just say, well, give me her average left arm blood pressure level, and that's my best prediction for what her left arm blood pressure level is. I wouldn't need to know what her right arm blood pressure level is because apparently there's no, well, there might be a correlation, but there's no linear correlation. Okay. Um, that's what we're going to do here. So all we're going to do is take the average y value. And if you're lucky, your calculator, when you go to one variable statistics, will allow you to pick which column you're going to find one variable statistics for. Mine does not allow me to do that. Uh, when I do it, it always uses L1. So when you see this X bar value, it's the average from the data in L1. So 91.6 is coming from, that is the average of the ones in L1. What I want is the average of L2 because I want the average y value of L2. So I'm going to have to do it by hand. But if you have a calculator that allows you to change it, you can go to one variable statistics and find the average value in L2. Let me just see something. Does it give me, you can do, I'm sorry, hold on. We can actually go to two variable statistics, right? That's what that's for. Now we have two variables, right? So if you go to two variable statistics, bar is the average in L1, L1, and this is all the data for L1. And, oh, I'm sorry, I didn't press variable. Okay, so there you go. And then if you scroll down, so this is all L1 data. And if you scroll down, it gives you Y bar. So this is the average of L2, right? So 156.4, so that's the average of L2, which is what I wanted. So you could do it that way. And you can see in MyMathLab, that is the prediction that they make. Okay, 156.4. Not getting this prediction here by plugging 90 into this regression line. They're not plugging 90 in for the X here. Simply taking the average Y value. And again, the reason they're not plugging 90 into the regression line is because we tested this sample and did not, the scatter plot for this did not form a line, right? When we looked at the hypothesis test. Okay, let me show you one more and then we'll call it a day. Okay, so I'll just look at one of these, like this one. So in this one, what they did is they said you have IQ scores were obtained for 20 randomly selected sets of couples. So I guess married couples, okay? And so you've got pairs of people here, right? You got uh, two couples IQ scores. There's 20 of them, and one of them is X and the other is Y. I don't know exactly how they separated the two. Oh, it says X represents the IQ score of the wife. So X bar would be the average IQ score for all the 20 wives, and Y bar would be the average IQ score for, I guess, the husbands. Okay, so let me just make a note of this so we don't get confused. So this is the wife's IQ scores and husband, apparently. Okay, they didn't give us the sample data, but there's 20 of these, right? There's 20 ordered pairs, right? Wife's IQ score matched with their husband's IQ score, and there's 20 couples here, right? Didn't tell us what those ordered pairs were, but they did tell us what the average was for this column and this column, right? X bar and Y bar. Okay, so again, this is the average IQ score for the wives, the 20 wives, and this is the average IQ score for the 20 husbands. And then calculated R for us by plugging, getting into that formula that we talked about earlier. So notice R is close to 1. The p-value, they figured out what the p-value would be for this, and it's 0.000. And this is the regression line that they came up with based upon the sample data. Okay? And they say find the best predicted value of y hat given that the wife's IQ score is 90. So you're kind of making a prediction for the husband's IQ score based upon the wife's IQ score being 90. And they say use a 0.05 significance level. So the first thing we need to do is make sure that the data forms a line before we use the regression line, right? If the regression line is valid, you would just plug 90 in for X into here and figure out what Y is, and that would be your best predicted IQ score for the husband. But we need to know whether the regression line is valid, and that, of course, that we have to test and see whether we have a linear correlation between X and Y. So I'm now going to do the informal test. We talked about this last time. Instead of doing a formal hypothesis test, you could also do this kind of informal hypothesis test, where you just look at the R value that you're given and compare it to a critical value that comes from a special table called the Pearson critical values. I can almost tell you right offhand, you can look at this, R is close to 1. I would bet that this is close enough to 1 that we can probably think of it as being aligned, all right, having a linear correlation. But let's do a formal test, this informal test and look at the critical values. So they say test at 0.05. So 0.05 would be this column, and N is 20 in this case, our sample size. So if you look at 20, we get 0.444. And then our R value was 0.9 something, 0.906. Now remember, the way you do this with this informal hypothesis test, it even tells you on the right-hand side, in case you forget, this is testing, with a null hypothesis of rho equals 0 against an alternative hypothesis where the rho is not 0. To reject null hypothesis if the absolute value of R is greater than the critical value given in this table. So you have to take the absolute value of R And of course, in this case, the absolute value of that 0.906 is still 0.906. The reason you're taking the absolute value is because if R, let's say R was negative 0.906. Now remember, R could be negative, right? It goes from -1 to 1. This is close to -1, which means it's probably forming a downhill line, right? But the tables don't have the negative values in it. The table that they give you, the critical values they give you in the table are all for positive values. So they just want you to take the absolute value of R just to make sure that you turn this into a positive number if it happens to be a negative. But for us, it's already positive, so the absolute value of this 0.906 remains at 0.906. But here, would be changing it into positive 0.906. And then you take this number, after you taking the absolute value of it, and you compare it to the critical value. And in this case, it's larger, right? The absolute value of R is greater than the critical value. And according to the table, if the absolute value of R is greater, then you reject the null hypothesis, right? Reject null if the absolute value of R is greater than the critical value. And that's exactly what's happening. Okay, so we're going to reject the null hypothesis, which I didn't write down, but so you're rejecting this here, right? And remember, this means there's not a linear correlation. So it means there is a linear correlation. Okay, so when I reject the null hypothesis, in essence, I'm supporting the alternative, which happens to be supporting a linear correlation, right? So yes, there is a linear correlation. Again, I think we kind of already knew that because this is close to 1. Okay, it's 0.9. But this is just verifying that, okay? Running the test. So anyway, well, in this case, as opposed to the last one, in this case, the regression line seems to be a good model for what's going on here with the ordered pairs from our sample. So now, yes, if you want me to predict the best, the best prediction for the husband's IQ score, if you're telling me the wife's IQ score is 90, and it's not, I'm not just going to randomly pick, I'm not going to pick the average Y value, because apparently the wife's IQ score has some effect on the husband's IQ score. And there's a linear correlation. So, and this is the, model for that line. So anyway, so you would plug 90 into the line this time, right? So let's just do that and see what we get. So it's going to be 90 times 1.22. Let me just write it out to be clear. So here's your regression line. And then I'm plugging 90 in for the X value here, right? Okay, so 90 times 1.222 minus, I think it was 21.31. I just double check it. Yes, negative 21.31. And get 88.49. And that's where they're getting this prediction from. So that'd be the best prediction for the husband's IQ score if the wife's IQ score was 90. The other thing I want to mention here is something called interpolation and extrapolation. Um, interpolation is when the x value that you're making a prediction for, like in this case 90, if that number is contained within the range of your x values from your sample. So remember, they sampled 20 women. If you look at the IQ scores for the 20 women, they might go from 80 to 120 or something. So that would be the range of your x values from your sample. So 90 is within that range. And so this is called interpolation when that happens. We're okay with interpolation. If this number falls between the range of the x values from your sample data, the women's IQ scores, or the wives' IQ scores, then interpolation we're comfortable with. Let's say 90 landed outside of the IQ scores. Let's say the women's IQ scores ran from 100 to 130 from the sample data, the 20 wives IQ scores. If 90 is not within that range, then it's called extrapolation. And extrapolation is a little dangerous because you don't know if it continues to be linear outside the range of the x values that you got from your sample data. So I would be cautious about plugging 90 in to the regression line if the 90 is not within the range of x values in your sample, because then you're doing extrapolation. You're assuming that this line continues to describe the behavior of the data, even though it's no longer, even though this number is no longer within the range of x values from your sample data. So that's called extrapolation. We usually don't do that unless we have no other way of making a prediction, okay? Because you're assuming that it continues to be a straight line outside the range of your sample data, and that can be a bad assumption, okay? In this case, they didn't tell us what the numbers were. They don't give us the 20 x values for the women's IQ scores, the wives' IQ scores. So we don't know what the range is. So I guess we're just going to assume that 90 is within that range, and we're doing an interpolation here. I'm assuming that's what they want us to do, but we don't know, right? Because they didn't give us the 20 x values. So we don't know if this 90 lands within the range of the given x values here from the sample data. But anyway, I just want you to be aware of that in case you ever run into something like that. Okay. Having said that, I guess we're pretty much out of time. Does anybody have any questions about anything before we sort of wrap it up? Okay, so I guess if you have any questions about anything, just email me and let me know. Next week is the last test, test 4 over chapter 9, 10, and 11. That's going to be due on Wednesday. The final exam is due on Thursday. Thursday is the last day of class, so the homework is due also by then. And I guess we only have one more section to cover, and we'll do that on Monday, right? We'll cover section 11.1, okay? Monday at 1, okay? All right, so hopefully I'll see you then. All right, have a good weekend. Bye-bye.